Next on the program, we have Good Fences Make Good Neighbors by Trond Hjorteland, who's a senior consultant at Scienta. Trond also has mantra. Great products emerge from collaborative sense-making and design. Don't forget to post some questions if you'd like, and I will address them later on. And let's begin, Trond.
Thank you. And welcome, everybody. Good evening. I want to actually address the audience online as well, say good morning, or good afternoon, good night, maybe even for you. I have to be honest, and I'm not going to look at the lens, because I'm tired of looking at the lens during presentation. So I'm going to look at the people in the audience there tonight. When I can see you, that is, I have to move forward to see you. So for those of you who were at the previous presentation by Marco, you got a heads up what I'm going to talk about. And it's not going to be make IT evening asset. That's just a company slogan. It's going to be about good fences make good neighbors. So Marco alluded to it a little bit in his talk, saying that if you have a small team, if you're like him alone and another designer, you probably you don't have to be good neighbors necessarily because you're good friends already and you're collaborating well as you do. But if you grow, if you go beyond, say, for example, a team size of 5 to 10 or something like that, you need something to so that you can collaborate in a good way, so you don't step on each other's toes, if you like. And I've done a few of these similar talks about modularity, as this proverb alludes to, but I'm going to take a little bit of a different spin today. I've been very fond of, interested in system thinking lately, and specifically the sociotechnical kind. So there's going to be a lot of that today to sort of enhance the thing, because there was something that Deepo Hill said. He tweeted a few months ago, a year ago, something. He said that software development is inherently a sociotechnical enterprise. I mean, the strands are not separable in any way, those two strands. Because we write software, we are humans writing software for people. So, people writing for people. So it's an inherently social activity, what we're doing. And I find that we often, unfortunately, focus too much on the technical part. I'm not saying that that's not necessary, of course it is, but it's not sufficient. We need also to focus on the social aspects of things, both for us as developers, but also our clients, the users, and the wider field, if you like. I'm not going to go too much into that, but we also have to take into consideration your home life, the people that you're creating software for, how they are behaving in the environment, what sort of influences they have, and all that. So the field can get really big simplicity. Because I think we frequently use a mechanistic model, if you like, a machine model. You've probably seen that. I'm going to go back to that later on, of course. And I think that's too simplified. It works in an ordered system, but we are working in a very complex system. So when I would try to find a good sort of illustration for this good fences make good neighbors, I picked this picture actually which is close from where I grew up on the west coast of Norway, in the rural area. So we see these stone fences all over the place. They are very common thing. And the thing is that they are put there for a reason, and they are not walls; they are fences. And they are not supposed to be like keeping people out, for example. They're going to keep wild stock, so your wild stock out, preferably, and your livestock inside, for example. And also use them to separate where one farm starts and the other one begins, right? Sorry, one farm starts and another one begins. So it is a boundary that we put in for a reason. And also in Norway, we're very fond of something that we call allemannsrett, which basically means the freedom to roam. In Norway, it's very important to us. So when you go in the countryside, you shouldn't be blocked anyway. You should be able to cross other people's farms, for example. So they should be climbable, these walls. They should allow communication and movement, even. So that's the idea. It shouldn't be a silo, it shouldn't be a wall, it should be a fence. So they clearly say what's in and what's out. And there is something that this guy said, which I sort of took to heart. Mr. Fuller, he said for the following: you have to remember that any boundary is a usual fiction. And this is important. Boundaries doesn't exist in the real world, really. We design them in, like countries, for example. There's something that we put in for a reason. And we have to use that consciously. We can't just haphazardly do this stuff. We have to be conscious about doing it. So they are designed. They're put in place for a concrete reason. And as I said, that we use the sort of mechanical model. So for us, it can be easily seen that, okay, we'll create a machine and there's a clear boundary there. There's something in the machine and there's something outside the machine. There's a tight boundary. But the thing is that when we create social system, those boundaries are not that hard anymore. They are quite open, as we are going to get to later. Sorry. And I think we underestimate how hard this is. We have done modularity for a long time, way back, but we still struggle with this stuff. There's a reason why, for example, you're here, probably listening to some quite old guys getting old at the moment, still talking about this stuff. So why is it that we need it if it's so hard? And I'm going to give you a couple of examples of this. I'm going to start actually with psychology here. I love this illustration saying what multitasking is. Like, you're jumping between things all the time because you want to compartmentalize things. You don't want to do all the things at once. You're going to say focusing on one thing at a time. So you in a sense compartmentalizing the thing. So it is a coping mechanism for us. And then we get into you probably heard about this, cognitive load. For those of you who have read the team topology book, probably familiar with these terms. So and the idea here is that there is a limited capacity to our mental memory space, if you like. So, and the problem is that since this is a limited space, if you overload it, things start to happen. We get stressful, we probably inhibit learning, we make errors, we do perform badly if you do overload these things. I'm not going to go too much into this now, so I recommend actually to look up the team topologies. They describe this very well. They take it to a team level, of course, not just an individual level. And what modularity does is let's see if this works. No, they would have to do it here. So the intrinsic load here, which is the inherent sort of complexity of the domain, if you like. This is something that we're going to look into when you do modularity. The extraneous load is not as relevant because that is the extra work that you have to do to sort of learn this thing, the stuff that you really don't want to care about. And the domain cognitive load is that how familiar is this to you? And both intrinsic and domain is something that we're going to look into today. How can we help you when you're working in a domain, in the subdomain, for example, that you can learn easily what is coming in as new, but also keeping away and don't have to think about all of the rest of the stuff, right? So that's the sort of the cognitive aspects of it. And the second part I'm going to get into is teams. As I mentioned in introduction, is we want to put in boundaries so that teams can collaborate better. So we want to actually reduce that interaction between the teams. There shouldn't be a hard dependency between teams because things take longer time, and you get a worse result probably because of it. So that is so not only to make them collaborate better, but you also can scale the organization better. So there are two things there. You can scale the organization better, and you can make them work better together. The scale, because of course you can just add teams. But if you're just going to add teams, they have to be independent of each other. They have to lose less coordination cost between them. But the teams, in order to make them autonomous or semi-autonomous, or what I call it, they have to have an area of responsibility that are theirs. So they have to own their own data, for example. They have to own their own tools, and they have to own their own processes. And it goes for all these teams, right? So, okay, let's say if you have this image, let's say we want this teams, the glorified team separation, semi-autonomous teams. But finding these boundaries as I said earlier, that's the hard part. I remember I've been doing service-oriented architecture for quite some time, and Udi Dahan is very adamant that is the really hard part, is finding these good boundaries. So if you want this autonomous product, biz DevOps teams, we have to be good at this to get this going. And there's actually some research on this called sociotechnical congruence or mirroring. You probably all heard of Conway's law, which is illustrating the problem if you don't get this right. So sociotechnical congruence or mirroring say that you should try to get how team works and what they're doing congruent. They should be aligned if you want to be effective. Another thing that semi-autonomous teams, that it will also enable parallel work. So you will speed up, ideally, if they work independently, as I said earlier. So the business will see that we move faster if you get this right. You get a shorter time to market, for example. By removing the obstacles, which is the integration between the things, the coordination costs between the teams. But we are probably used to running around in situations like this. And this is a wonderful quote from the Big Ball of Mud paper from 1997. Sadly, architecture has been undervalued for so long that many engineers regard life with Big Ball of Mud as normal. I've been there, working on a huge system, millions of lines of code, were even proud of how large it was, entangled as it was. Everything was connected with everything. So, and you get this, of course, this classical Big Ball of Mud, which is the paper, the name of the paper. So the business agility actually then is constrained by the technical agility. So you have a big ball of mud that is all entangled. You can't move fast, business-wise either. You can't be agile if you fight your architecture, put it that way. And yes, I'm going to mention. Yeah, of course, there are some technical concerns, but I'm not going to get into those now. These are the ones I want to highlight today. And yeah, so with modularity, we kind of feel that it works. It should work. But we actually have data now, especially from this great book, Accelerate. And I picked this one quote because it serves my message today. It's a loosely coupled, well-encapsulated architecture is the biggest contributor to IT performance, even larger than test and deployment automation. And that is saying something coming from the Accelerate book with these DORA metrics. So it is an essential part of your architecture. And I think it was, I don't remember her name, but there was a doctor who has done some research on open source, for example, here. And she actually claimed that open source is a perfect example for when modularity works well. When people can work in separate parts of the world and still deliver the same product together. Then you have probably a good modularity in your system. So generally, I use a couple of soft architecture and a structure, old structure to match is also something they say in that book. You need that sociotechnical congruence against, as I mentioned earlier. Actually, some research I read about sociotechnical congruence is that showing that if you get this right, you can get a 30% decrease increase in productivity. And that is a considerable number. Or actually, 30% reduction in resolution time is actually what they measured. And we got more research. This by Dr. Callis Baldwin. She talks a lot about optionality and real options, if you heard of that. So she said that if you have a modularity, you multiply your optionality enormously while doing that. So, and she said what she's saying is that it is the recombination and combination of modules is the new game. She has illustrated this in this thought experiment, where she has said that if you have a number of modules and a number of experiments that you can run with each models, and she said by this thought experiment, you will get a 20 times increase. And that's a huge number. Of course, it's a thought experiment, so it's not real data. But what she says that the value, I mean, doing this, of course, is costly to modularize in this way. And also just doing it and maintaining it and testing it and all that. But she said, but a value multiple of 25, we pay for a lot of engineering cost. So there's a lot of optionality here. So it's not only that we move faster and all that, but it creates option for us in the future by the recombination of modules. But now you may wonder why I have a picture of a kids' party here. I love this illustration. This is probably Dave Snowden I got this from. Saying that complexity, if you have had a kids' party at home, you can prepare as much as you like and think you have everything in control. When the kids are in the room, all hell breaks loose, normally. So it's a really complex environment because you can't predict how it's going to turn out. You can try it with project plans, as Dave Snowden said, but it's an illusion of control. So that's a thing I'm going to touch a little bit upon today, is that we try to, when we modelize even, we try to, it's a very classical thinking. We can decompose and sort of into components and then reconstruct a whole afterwards. But that is very classical thinking. It's a reductionistic linear way of thinking. So And probably we like to think that way, at least I do, because I have a science background. And you probably all of you have similar backgrounds, or most of you, like a STEM background. So you are sort of drilled into that reductionist thinking. But the world, especially if you include people in it, as a social technical system is, it gets complex. So, but I'm using the reductionist machine model to illustrate this anyhow. Can you, based on what I said, what is the problem with that illustration? Anyone, do you see any problems with that illustration as a system? Anyone? Hands? Yes. And also, it's very predictable, right? It's stable. If you turn one dial, everybody else is going to turn. It's going to be predictable. It's going to be linear. The problem is that when we modularize, things that then happen is that, is that we are using the machine model. We assume determinism and predictability. But say, for example, if something happens there, somebody decided to change one of their components or change the different how they work. Maybe they changed to REST interfaces instead of SOAP interfaces. Maybe they went for a product organization instead of a project organization or something like that. So you see, the parts here, they are not predictable. They are not stable over time, which means that you can't, when you do modularization, you have to be aware of that the parts that you have decomposed, they will change over time. And also, if you look at the parts in isolation, doesn't mean that you optimize. For example, like they did here, created a fancy new cog. Doesn't mean that the whole is getting better. Yes, the parts are getting better, but it doesn't mean that the whole is getting better. This is the insight. For example, Akov talks a lot about, Russell Akov talks a lot about this. So we are inherently trying to do system design here. And I love this quote by Ruth Malone. I think it was a tweet. So we're going to go into that a little bit. So architectural design is system design, as she said. Architectural design is system design. So system design is contextual design. It's inherently about boundaries, what's in, what's out, what spans, what moves between, and about trade-offs. It reshapes what's outside just as much as it reshapes what's inside. So you see, there's a lot of things going on here, just in this simple tweet of hers. So if you go back to this illustration then. So let's define what a system is. She said system design, let's define what a system then is. I'm going to start here off with Russell Akov's definition. He says that a system is a system with two or more parts. It has to have more than two, unless it's not a system, right? Because it has to have more than one parts. But it has to satisfy three conditions. One, the behavior of each element affects the behavior of the whole, as this illustration clearly shows, right? If you turn one wheel, you're going to turn the rest, and the whole is going to change. Number two, the behavior of the element and effects on the whole are interdependent, which means that one dial they turn, which will affect other dials as well. So it's not only affecting the whole, it's affecting everything else, and of course then also the whole. So everything is, this interconnectedness is really enormous here then. He also had a third one, just to be a real academic, is that he says that you can't create an independent subsystem because they are, again, interconnected. So if you have an independent subsystem, that's another system. And if it's independent, then it's not part of the bigger system. But still, if you have this system, they are hierarchical. So it's all turtles all the way down kind of thing. Right? Parts belong to parts and parts. You can break it, decompose it all the way. So this is very hierarchical then. So a good quote from Akov there is that a system is never the sum of its parts, it's a product of their interaction. And if we go back to the machine model, a machine, your car, for example, unless it's a very fancy car, say it's an old car then, just make it simple. You can define how that car behaves just by looking at the parts. It's a machine model. So the parts, the whole is then a sum of the parts. But as Akov say, a system really should be larger than the sum of the parts. So what is that thing that makes it larger? We're going to get into that later on. Another well-known system thinker that you may know is Donella Meadows. She has a good quote, or as a definition of our system. It's a set of interrelated elements organized to serve a particular function or to seek a particular goal. And this is really interesting. But because it's not a system just sitting there. It actually has a purpose. It's purposefulness. It has something you want to achieve as a system. It could be something that we put, the purpose could come from outside, like for us, for some driving a car. The car is a system, yes, but we put purpose on it because we use it. So the interesting part of this is the purposefulness, and that changes the former definition I had about the system earlier, Michael. But he also went there, but he was very adamant that he used a lot of the former definition. But he has sort of characterized sort of different types of system based on their purposefulness. Use that word. So he's looking at the parts and the whole. So you have a deterministic system. The parts have no purpose. Like your heart doesn't have a purpose. You as a system have a purpose. Your carburetor in a car doesn't have a purpose, but a car is given a purpose. That's a whole system. Right? So, so neither the parts nor the whole is like in a car has a purpose. But we get interesting when we get animated. As I mentioned, a person, your heart, doesn't have a purpose, but you as a human being have a purpose. And that changes things a lot. This is not just a tweak, this is an enormous change. We go to another type of system, it's a social system, which is then basically a group of people, for example, your teams, your company, that's a social system. And then, of course, your parts, yes, you are human, have purpose, but also the company has a purpose. And they are intermingled, those two. They should be at least intermingled. So when you work for a company, you don't want to, I guess the company don't want you to have a different purpose than the company. Or vice versa, right? You want to be a part of a company that you're proud of, and then you want to be aligned. Your purpose will want to be aligned with the company. So you're a social system, in that sense. He also goes into the next level, which is the ecological, which is the environment, where the parts have purpose, but the whole doesn't necessarily have a purpose on its own. Like, for example, humankind, for example, doesn't necessarily have a purpose. So if we go back to this model then. So each part here have people in them, which makes it then, we're back to what I said earlier in the beginning, that this is a social technical system. It's not just a deterministic system, as I showed before. It has people in it, and it has actually it's a social system, which means that it's a social technical system. You can't divide those two. And that makes modularity a lot harder. Because I mentioned earlier, if the parts change, if there are people in it, people change all the time. They're not stable. They're not cogs in a machine. So there you see this model breaks down when we put people in there. And also because, as I mentioned, that people have purposes, and that also, of course, because it changes the whole picture quite dramatically. And they are not necessarily aligned as a local representation, as I showed earlier. So what we're dealing with here is actually something that is called an open system. Russell Ackoff, probably pronounced Ackoff, really. When he was illustrating stuff, he was really often using the sort of the machine model as that, sort of the deterministic model, just to illustrate his points. But an open system is very different from a closed system. As I said, I have a science background, and as a scientist, as a physicist, you love to create closed systems because they're easier to deal with, because you don't have to deal with all the messiness of the environment, right? Like, for example, the laws of thermodynamics, for example. It works in a closed system, but it doesn't work in an open system. In an open system, you can actually have negative entropy instead of increasing entropy. So having taken a different framing from the closed to the open system has a very dramatic effect. For example, a team here then. It's not a closed bubble. It's not a closed system. It's an open system with permanent boundaries. So they are affected by everything around them, even their home life, their kids, commuting back and forth to work, having been forced to get back to work after COVID. I mean, everything plays a role here then. So you can say, if it is so open, how can we control this messiness then? That's another good quote from Ackoff. So it's the consequence of this interconnectedness. I really like this quote because he said our system is more than the sum of its parts. We discussed that, especially if you have a social system. It's an indivisible whole. It loses its essential properties when it's taken apart. What do we often do when we tackle a problem? When we want to modularize it? We decompose it. We take it apart. And we look at the parts in isolation. It goes quite against what Ackoff is saying here. You're ruining the system by doing that. So if you believe that you can decompose the system, understand the parts, and think then you understand the whole, you're mistaken. And that's what I think we often fall into that trap. Of course, we have this machine model. We think it's as simple as the cogs, as the illustration here. So we are doing something that was often referred to as reductionism, where we actually then decompose the system, explain the parts, and then based on the parts, explain the whole. But we need another approach, and this is what system thinking brings to the table. We need synthesis as well, which is actually pretty much the reverse of analysis. Then we go wide first, and then go low. So what you do is actually, if you want to understand that system that you're going to build, you have to understand what is that system part of? What is the containing whole, if you like? I often use the example of a car again. So if you break a car down, you can put it back together again. It's a functional car. But how do you know it's actually a car that people want to buy, for example? You have to understand where it's going to be used, how it's going to be used. You have to understand the wider field. So you have to go up, understand, and then go down. So you have to do both analysis and synthesis. Do this. So you can illustrate this. I said analysis focuses on structure, right? And it reveals how things work. Synthesis focuses on function and illustrate then why it should work, how it should work, why it should work. So how can you find this boundary? I kind of like this the idea of seams. I think it's Michael Fedders who introduced that. How can you? Is there a good place you can draw these boundaries? And looking for the natural seams is a good way. This illustration, of course, is the geological folds, so you can see the seams visibly. In a social system, it's not as easy, of course, as this one. But we still want to look for these natural fractures, if you like, or sharing layers. So there's a lot of names for this. But there are boundaries. As Marco said earlier, there are some. When he described the domain-driven design, you look at the business and see if are there any things that are core, for example, and what is supporting. You're getting an idea there are seams there then, natural seams. But these seams also exist in social system. I've done this talk before, and I did it just after the storming of the Congress in the United States, just to illustrate this about political factions. So social systems also fracture. They faction into bits, if you like. If they're stressed, they're going to fraction into two groups and subgroups. So how would this look? If you look at the political faction, how would this look in our line of business? And this is something I really like about Team Topologies, is that they take this on board in a really subtle and interesting way. So they see that, okay, if you look at these team types, what they're actually creating then is attractors to people. If you want to work on business level in things, join a stream-aligned team. If you want to help teams to get better, join an enabling team. If you're really into AI and machine learning and complex stuff, work in a complicated system team. If you want to work on technical stuff, if you want to create a platform, well, join the platform team. So you see, they have actually subtly then used this interest that we have, inherent interest, to lure us into different teams, into different factions. So this is a good natural seam, if you like. But how have we done this traditionally? And you probably know this guy, especially the paper title there. This is David Panas from his paper from 1972, where he said this paper discusses modularization as a mechanism for improving the flexibility, comprehensibility of a system while allowing the shortening of its development time. I often use this quote and just took away the paper and try people to sort of, could they see how this relates to what we're talking about today? I mean, you could say this about microservices, for example. It's the same idea. But he also says, this is really important, the effectiveness of modularization is dependent on the criteria used to divide the system into models. So you can't just hack away. There are, again, you have to look at for these, call them seams or whatever, there are certain ways that works better than other, and how to find these then. Of course, he has an idea in this paper, and his quote says instead, what this has become known as information hiding. So they say, we propose instead that it begins with a list of difficult design decisions, which are likely to change, and then hide them within the modules. Because then, of course, you will reduce the blast radius of a change, because then the change is going to happen within that component. So this is what later gave us object orientation and all of the good stuff in encapsulation, all that. But the thing is, this is emergent, though. It's hard to predict this up front. You have to sort of go in there and try and work your way towards this. Foot and YODA had a similar approach, but they looked at more like probably similar to layers. Illustrated here by house. What sort of parts of the architecture changes more frequently than others? So, for example, the site here is probably very stable. The structure is also fairly stable, but less stable than sort of the underlying foundation. The skin of the outside of a house may change. You might change boards and some rotten and all that stuff. So they change more often. And then, of course, you get into in the interiors, change all the time if you move furniture around and stuff like that. So that is more layers, if you like. So in our line of work, it could be like separation between data and code, for example. Data changes often, code less often. There are parts of code that change more frequently than others. So that's a way to look at them. Let's look at the themes, what changes more frequently. Interfaces, implementations, and stuff like that. And also think bimodal IT, for those who know that. I know Simon Worley has something that must say about bimodal IT is that there is an assumption that the front end changes more frequently than back end, so then it should be different. So there are different ideas there, but again, it's still it's an emergent thing. It's not something that you can plan ahead. It's something that you sort of build up. So it's a bottom up. It's something that and it's a moving target often then, because things when you start building stuff, it changes and the requirement changes and all that stuff. You have to. So this is where agile fits very, very well. So and hence the principle from agile is that the best architecture, requirements, and designs emerge from self-organized teams. So again, it's a very bottom up type of approach. But I think we need also that top down. Even Fred Brooks said that was the most important thing. Now, Fred Brooks also is the guy, the man-month guy. He also said that there should be one or a few architects that do this. I don't believe in that, but we need something that takes the holistic view as well. Yeah. So this is where system thinking and the synthesis, as I mentioned earlier, comes into play then. So, but I have an extra claim, and there might be a subtle difference, and I'm not convinced that it is a good difference, but I see that there's a difference between top-down and outside-in my perspective. I know you wonder why I have 2 marks here. And this is just to illustrate that you can get ideas from the not unlikely places, but still. This is from literature. This is the Name of the Rose. This was the miniseries, BBC miniseries. Can really recommend it if you like the book, because this series is close to the book, as you get. And they quote the book literally in that book. There's no rewrites. And this quote caught me. Thus God, and just to okay, before I read the quote, I'm going to give you the setting. So William here, Friar William, and his novice Ada, what is it called again? Atsu, sorry, I forgot his name. They were looking for a book in a library, and the library is a maze, and they're trying to find a way through this maze, and they can't find a secret room. So then William gets the brilliant idea, we have to go outside. We have to look how the structure looks from the outside to figure out where that room could be. And that's what they did. And then he pulls this quote, is that, thus God knows the world because he conceived it in his mind, as from the outside, before it was created. And we do not know its rules, because we live inside it, having found it already created. So it might be subtle, but I think we need to not just go out one level up, as I say. We need to understand why is the thing the way it is. Why is this? This is not only top down. We have to look at from the all perspective, all the perspective that can go wider than one level up. So it is a subtle. I'm not sure. I'm not 100% convinced, but I think that you have to have this out. So I separate between outside in and top down then. So let's look at some techniques. I haven't got time to go into many of them today, unfortunately. There is one that I like a lot, that you probably are familiar with, since it's not a .NET conference, but I'm sure you know of YODA and his service orientation approach. And he has a definition of something I really like, which is business capabilities. He said that a service is a technical authority for a specific business capability. And then, like domain-driven design, you take a business perspective. And this is the outside-in perspective as I see it. Because when you're creating an architecture design system, yeah, you want to see the whole, but you only want to see why the whole is going to be like it is. And that is the outside-in. So that's the business perspective. So business capabilities is a way to do that. I haven't got time to go into that, but I have other talks on that. So that's, but it is basically business architecture. Yeah. And of course, as Marco, if you didn't watch his talk, go back and watch it, because there's a brilliant way of introducing yourself all to domain-driven design by creating games. A wonderful way of doing it. So if you wanna understand, for example, this is the event storm thing again with Alberto Panlini. If you understand domain-driven design, please do check out Marco's talk. It's really, I can really highly recommend it. But what we're doing here in the big picture event storming then is like, we're trying to do that overview again, like the whole thing from start to end. We want to understand the whole thing, how everything interconnects, using events. It's a brilliant idea. Again, it's synthesis. We go up, we understand the whole, but I think it's also an outside in, because we give it a language, we give it a perspective. There are other techniques, of course. Domain storytelling is a good one. I am really fond of having a user perspective, so I like user story mapping, for example. So again, give you a different perspective, a different view of things. So if you want to learn more, there's this free book. I recommend you to check it out. I got 2 chapters in there on business capability mapping and user story mapping. And there's lots of information there about event storming and domain storytelling, a lot of good stuff. It's free, so go check it out. There's also techniques from system thinking. I haven't looked into them myself. There are soft system methodology. There are something called viable systems model, the idlest design, which is something that Akov came up with. And also you have sociotechnical system crowd, the open system thinking people. They have something they call the search conference and participative design workshops, which I also take this more holistic view of it, the whole thing. So I think emergence can work, and I think we've done that a lot. So, and it's, of course, it has proved itself in certain situations, of course. But I think we're bounded by the increments then. It's hard to stray off the path, if you like. Because we have to try something out. We have to see if it works, then refactor, maybe in a rewrite, and try again. So it takes a lot of iteration before you get it, if you like. So it demands that continuous rethinking and redesign all the time. And I think if you do, for example, a modularisation of a big monolith, for example, if you pull out services, if you like, microservices, it's easy to get going, but they're low-hanging fruits. And say, okay, this is going perfectly, and then you set several teams ahead doing the modularisation of this monolith, and then you run into the hard problems. And then you see, okay, what we did earlier made sense, but maybe it's not coherent anymore. So then you have to step back, and then maybe you can potentially fail, as I like illustrated with this broken pane of glass. So, and you can easily end up with a classical distributed monolith then, right? As you heard of. So how to cope with complexity then? I think I alluded to it, is that not only do we need analysis, as I said, we still need that. Don't throw the baby out with the bathwater. We still need analysis, but we have to do synthesis as well, and also the outside in. We need as many perspectives as we can get hold of, and as many people as we can. So collaborative modeling, as also the domain design talks warmly about, is essential today, because as I said, we're working in a sociotechnical system, and the way to deal with sociotechnical system is to make sure that we bring all the value out of people working there. They are the most resilient parts of the organization, or the whole system is you people working there. So involve as many people as you can. So you do the emergent tech design, do that, of course, do the bottom up, but also include the business model, the business design, the user needs, and even the wider field. As I mentioned, the participant design workshop from sociotechnical system thinking, or open system theory specifically, they actually say that if you're going to design a team, you're going to base it on a set of psychological requirements that you as people have. You want to be able to master the thing, you want to be able to evolve yourself, you have something that is reasonably hard to do, you want to be able to own certain things that are yours, you want to be able to connect what you're doing with your social life. You want to have social support at work. All those, there's a list of 6 of these so-called psychological requirements. So the whole participatory design workshop is based on that. If you're going to design your team, use these as a foundation. So again, you go even wider than just the requirements. So my advice is that you take this holistic design. I illustrate then, instead of that broken glass, that you take a rose window, for example, then. So do try to get this holistic view, add this to your tool belt, especially the open sociotechnical system design thinking, which is there, as I mentioned, the participatory design workshop and all that. So have an idea of where you're going, have a direction. You're not going to have a plan because that's not going to work in complexity, but you want to have a vision, you have something, an ideal future, if you like. How would this perfectly look like? You're never going to reach an ideal, but it's something that you strive against, and then actually moving at least in a direction that is coherent. There's a term from von Hjorteland, which is probably the guy who coined open systems idea. I think it was in the 30s, but his book came after the war. Something they call equifinality, which basically means that there are different ways to the same goal. There isn't one path to what you're going. There are different ways. So you can try, and you can adjust, and there's a lot of ways you can do to get there. Just be aware of that. In complexity, there's no one path to get to a system. So the perfect system doesn't exist, but there are different ways to get there. So if I want to summarize this talk in a sense, I would say that you need analysis, but you also need synthesis. You have to do the both. And how would you do that then? Because as I said, you go up and you go down. You do that once? No, you do it as often as you can. It's an iteration, this. There was somebody who described how you could describe the scientific method in this way. Say if you have this aha moment, I have an idea, this was funny, and you want to investigate what's going on in that. So you create a hypothesis, you go down, you analyze, do some studies, and then you go back to synthesis again. And you do this as a spiral. And this is similar to if you have that image, if you've seen Eric Evans' whirlpool model, it's the same idea, basically. You're doing the same thing. So analysis yields knowledge, but synthesis yields understanding. That's another Akov quote, by the way. So if we're going to end here now, I think we have to put this machine age thinking behind us. There are certain parts of systems where, of course, it works. If you want to create a physical system, use the deterministic model. That's perfect. But if you are working with people and it's a social system, you have to get out of that machine way of thinking. You have to be a system thinker, basically. That was what Akov is calling it. You have to move into the system age. And I specifically like, as I said, the open systems way of thinking, because even though you can create a system that is coherent, but it's closed, and the sum is more than the parts, but it still is. You can easily model it as a closed, but I think that's also wrong. You have to be aware of the environment, and we should embrace that. It's basically embracing complexity, if you like. So I think that if we be able to create these fences, then we can make a system that is more than its parts. And by understanding the connections here, and then how things works and the purpose of the system, we can make it produce, we can make the product of their interaction instead of the sum of its parts, as Akov had the quote. And with that, I want to thank you for your attention. Any questions?
Yes, thank you, Trond. We do have a question online that's from a bit earlier in your presentation. Natalia Remes is asking, can decomposing the system result in frequent reorgs, and how to avoid people fatigue in that case?
Exactly. So that's why you should take care. I mean, if you're in complexity, things are going to change. The parts are going to change. I didn't mention that, but there is an idea of something that they called organization capability, actually. So your organization shouldn't be believing that, okay, we have got these teams now. We got these perfect teams. We are set. We can just go. The teams are going to change. They are, because not only because teams themselves change, and then the other teams have to change, but also that the environment change and the business vision may be even changing. So you have to be adaptive. The whole organization has to be adaptive. So teams can't be seen as static. That's also something that team topology talks a lot about, right? You're looking at the interaction patterns between the teams, and then you have to maybe adjust the teams.
Thank you. Anyone in the live audience would like to raise a question?
I'm sure you have some. Don't be Norwegians. We don't like asking questions.
I think they're gonna ask you over the drinks later on.
Well,
That's
unfortunately,
a lot easier.
Unfortunately, I can't join you for the party. So if you want to contact me, the best way is actually on Twitter. I have to leave in just a couple of hours. But I'm happy to take questions on Twitter and LinkedIn and other places.
Thank you. Let's give a round of applause, Trond, for a brilliant presentation.
Thank you.